This is Section 9 of the SAT manual. Section 9 of the SAT manual is systems of linear equations. Systems of linear equations are fairly common in high school. They are also fairly common on this test. Unfortunately, a lot of students have a superficial knowledge of systems of equations. A lot of students have memorized certain processes that will solve systems of equations, and in most cases those processes will work perfectly well to solve the system of equations. But College Board will test systems of equations in a deeper way occasionally, and if you are not really familiar with what is underlying systems of linear equations, what's actually happening in systems of linear equations, if you don't have several conceptions of systems of linear equations, you're going to struggle on some of these questions. So we are going to take quite a deep look at systems in this section to make sure that we do have all of that underlying knowledge. Systems and their solutions. First things first, we've got to talk about what it means to solve a system of equations, and we should actually start with something even more basic, which is a little definition here. I would highlight this. A system of equations is a set of equations that you need to deal with at the same time. Occasionally, systems of equations will actually be referred to as simultaneous equations, and as you know, simultaneous means at the same time. So a system of equations or simultaneous equations are at the same time equations. We are in section 9 here going to deal solely with linear systems. The SAT will, however, occasionally test systems of equations that involve quadratics or parabolas, perhaps even circles. So there will be occasional questions where you have to think about or figure something out about the points of intersection between a line and a parabola, or maybe even a circle and a parabola, or a circle and a line. But again, in this section, we're going to confine our discussion to linear systems. And a lot of the stuff that we discuss in linear systems will lay the groundwork for some of that more advanced stuff that we might deal with later, parabolas, circles, and all that. So what does it mean to solve a simultaneous equation question or a system of equations? When we talk about solving a system of linear equations or finding the solution to a system of linear equations, we are talking about basically two things. There's two sort of definitions that you need to know. One is that you are finding and again, I'm going to highlight this, the values of the variables that make all of the equations in the system true. Usually you're just going to be dealing with two equations, but occasionally you will see questions that involve more than two equations. That is one definition. Again, the values of the variables that make all of the equations in the system true. The other definition is, if we're talking about the XY plane, when we talk about the solutions to a system of linear equations, we are talking about any points of intersection between the two lines. We're going to take a look at a couple of examples right now that will illustrate these definitions. So in example 1, which after I read through these directions, you may want to pause the video and do this on your own. The directions here say that we need to determine if the following pairs are solutions to this system. So in example 1a and example 1b, we are given a pair of values, one x value, one y value, and we need to determine if these values for x and y satisfy the two equations in this system. So again, pause the video, do this work on your own. So for example 1a here, I am simply going to plug the x value into the first equation, then the y value. So this equation becomes 2 times 3, which is 6, plus 1 minus negative 1 is plus 1. 6 plus 1 is indeed 7. So the first equation is satisfied. The second equation is going to be 3, that's the x, minus negative 1. That is 3 plus 1, which is 4. That equation, that second equation, is not satisfied. I got 4. The second equation says I'm supposed to get 2. So the pair of values 3, negative 1 do not work for this system. They do not satisfy this system. So 3 and negative 1 is not a pair of values that is a solution to this system. System is not satisfied. Now 5 and 3, let's take a look at this one. So now for the first equation we have 2 times 5, again substituting the 5 value in for x up here, minus 3, that is 10 minus 3, which is indeed 7. So the first equation is satisfied. The second equation would be 5 minus 3, which is indeed 2. Now the first and second equations are satisfied, which means that 5 and 3, an x value of 5, a y value of 3, is indeed a solution to the system that we are given here. So again, that example will serve very nicely, hopefully, to illustrate the first definition of what it means to solve a system, finding the values of x and y that do satisfy all of the equations in the system. And then the second definition that deals with points of intersection, if we take a look at these two lines, 2x minus y equals 7 and x minus y equals 2, plotted on the xy coordinate plane, we can see that they intersect at 5, 3, which is exactly what we just found in example 1 up here, that 5, 3, x, y, 5, 3, is a solution to the system, and 5, 3 is also a point of intersection between the two lines. Next page, we are going to talk about not yet about actually solving the system. We will get to solving the system in a moment. We need to talk about the possible outcomes of a system, what can happen when we are dealing with a system of linear equations. First, let's reiterate something that we have learned previously in section 8. There's actually a few places in the manual where we go over the common forms of a linear equation. One of them is slope-intercept form. Slope-intercept form of a linear equation is y equals mx plus b. Standard form, which again we have gone over elsewhere in this manual, standard form is ax plus by equals c. In terms of m and b, we have gone over this already, and you should already know that m is the slope and b is the y-intercept. And indeed, when it comes to determining the outcome of a linear system, the slope and the y-intercept will play a huge role in determining the outcomes. So here's what we're going to do in example 2. We are going to take a look at this standard form equation, and we are going to derive from it the slope, the y-intercept, and slope-intercept form. Now, for those of you that have done the section 8 video, you should be using your shortcuts here. You learned in section 8 that m equals negative a over b, where in this case you have got your a equaling 4, your b equaling negative 3, and your c equaling negative 8. So you know that your slope is negative a over b. You know that your y-intercept is c over b. So we are going to use those shortcuts. If you do not know those shortcuts, you should know them. You can also just do this algebraically, where you rearrange into slope-intercept form, y equals mx plus b form. That's perfectly fine, but the shortcuts are useful here. So we are going to do, for slope, negative a over b, which is negative 4, that is the a, over negative 3, which equals 4/3. So the slope of this line is 4/3. The y-intercept, again, that is c over b. So we are going to do c, which is our negative 8 over there, b, which is negative 3, and the negatives will cancel each other out, and we get 8/3. And therefore our slope-intercept form, just substituting 4/3 in for m here, and 8/3 in for b here. So our slope is there, our y-intercept is there, and now we have our slope-intercept form. In terms of the outcomes, again, the slope and the y-intercept will help us determine which of the three possible outcomes, I'm going to highlight that, which of the 3 possible outcomes we are dealing with. Let's take a look at how we can use slope and y-intercept to determine which of the outcomes we are dealing with. So in this box here, we have determining the outcome of a linear system using slopes and y-intercepts, slopes and y-intercepts. So we've got 3 sample systems, one here, one here, one here. In the first system, we can clearly see that we have a single point of intersection. These 2 lines are intersecting at one point, so there is also one solution. So let's write that down here. There is one solution, one point of intersection. And we can see clearly that the slopes of these 2 lines are different. They're different slopes. One actually has a positive slope, one has a negative slope. So that's what I'm going to write here. I'm going to write different. We could find the slopes from the system using algebra or using the negative a over b shortcut, but we don't really need to do that. We can just look at the lines and see that clearly the slopes of these lines are different. When the slopes of the 2 lines in the system are different, you will always have one point of intersection, one solution. The y-intercepts are completely irrelevant, so I'm going to write a n/a for not applicable here. It doesn't matter what your y-intercepts are. If your slopes are different, you're going to have one point of intersection. You can see that these 2 lines in this system do indeed have different y-intercepts. However, you could have one line and another line that have the same y-intercept and therefore intersect on the y-axis. So as long as the slopes are different, doesn't matter where the y-intercepts are, the 2 lines are going to intersect one time. There's going to be one solution. Down here, we're going to write 2 intersecting, just write small, 2 intersecting lines. I highly doubt that you are going to see the following terms show up on this test, but I am going to write them down anyway. When we have a system of equation that results in 2 lines that intersect at one point or that have one solution, we say that the system is consistent and independent. Again, I highly doubt you're ever going to see those terms show up on the test. I'm just throwing them out there in case. Next scenario over here, you can see that we have 2 lines that never touch each other, and therefore we have 0 solutions or points of intersection. We should be able to see just by a quick visual examination here that the slopes of these 2 lines are equal. So I am going to write same here, same slopes, and the y-intercepts, this guy and this guy, they are different. The y-intercepts here are different. So same slopes, different y-intercepts, and down here at the bottom we are going to write parallel lines. That's what these lines are. They are parallel to each other. When we have a system that has no solutions, we refer to that system as inconsistent. Again, probably are not going to see that terminology, throwing it out there just in case. Finally, we have this third system over here on the right, this third possible outcome where every single point along one of these lines or the other is going to satisfy the system because these 2 lines are exactly the same. So we have an infinite number of solutions. These 2 lines are the same, which means they share all of the infinite points on each line. So we have an infinite number of solutions or points of intersection, and in this case, since these are the same line, we need the same slope, or we have the same slope, and we have the same y-intercept. So when our slopes and y-intercepts are the same, we will have the same line. And the technical name for this, again, probably won't see it, is probably won't see these terms show up on the test: consistent and dependent. Consistent and dependent. Those are the 3 outcomes of a linear system which you can determine using slopes and y-intercepts. If you have the equations of the 2 lines, you can find the slopes of those lines, you can find the y-intercepts of those lines, and you will know whether you are dealing with 1, 0, or an infinite number of solutions. These are the 3 possible outcomes for a linear system: 1, 0, infinite. On the next page, we are going to put this into practice. In example 3, we are given line P that has this standard form equation. Again, that's ax plus by equals c. And we need to know how many points of intersection there are between line P and the 3 lines that we were given down here in examples 3a, 3b, and 3c. If you understood the material on the previous page about the outcomes of a linear system, you should be able to do these on your own. So pause the video. If you're a little bit shaky and you want to watch me work through it, I'm going to do that right now. So I am first going to determine my slope of line P and my y-intercept of line P using my negative a over b and c over b shortcuts. So a in this case is 3, that's the coefficient in front of the x. B is negative 6, that is the coefficient in front of the y. So my slope is 1/2, that is the slope of line P. My y-intercept of line P is going to be 8 over b, which is negative 6, and that is going to reduce to negative 4/3. Negative 4/3 is the y-intercept of line P. Now in example 3a, again, let me do negative a over b for this line, and that is going to be negative 1. There's a negative 1 coefficient there in front of the x over 2. So I know that my slope is 1/2. So right away, I can see that the slope of the line is equal to the slope of line P, which means that at the very least, I'm not dealing with one point of intersection. I'm either dealing with parallel lines having the same slope, or I'm dealing with the same line. And in order to differentiate between the two, I need to know my y-intercept. So again, this was the slope. Now the y-intercept, c over b. So what is that here? That's 5 over 2. 5 over 2. So I have same slope, 1/2, different y-intercept, 5/2, negative 4/3. Remember from the previous page, that means we are dealing with parallel lines, which means there are no points of intersection, there are no solutions. Next, in example 3b, again, I'm going to determine my slope. And in this case, my a is negative 2 and my b is positive 1. So my slope is 2. I don't need to go any farther. I know that the slopes are different. This is 2. This is 1/2. When the slopes are different, we are definitely going to have one point of intersection or one solution. The third equation is already in somewhat in slope-intercept form. So I'm just going to separate out that 1/2. I'm going to pull that 1/2 out in front of the x just so it's in my m position, and the y-intercept will be negative 4/3. That's just that right there. So I can see in this line I've got the same slope, 1/2, same slope as line P, and I have my same y-intercept, negative 4/3. These are the same line. There's no difference between these lines. They have the same slope, same y-intercept, they're the same line, which means I have an infinite number of points of intersection or an infinite number of solutions. So again, that is how we can use slopes and y-intercepts to determine which of the 3 possible outcomes to a linear system we are dealing with. Here are a couple of other variations that will probably look a little bit more like the kinds of questions that you will get asked on the test. So in example 4, again, if you have understood the previous material well, you might want to try this one on your own. In example 4, we are being told, both up here and in the question, that there are, I'm not going to circle that actually, I'm going to underline that there are infinitely many solutions, and we are being asked what the value of C is. So remember, when there are infinitely many solutions, that means the slope of one line has to equal the slope of the other line. It also means that the y-intercept of one line has to equal the y-intercept of the other line. So I'm going to label this line 1 and line 2 just so it's easier to talk about them. And now I am going to go about finding my slopes and my y-intercept. So in terms of the first equation, I am I'm going to rearrange this just so that it looks a little bit more like slope-intercept form, just so it's slightly easier to deal with. So that's now my first equation. I can see that the slope of line 1 is going to be 1, right? That is just the coefficient in front of the x, which is my slope. And in line 2, I'm going to use negative a over b. I do have to be very careful here because the x and the y terms are flipped. In other words, this is not in pure standard form. So my a is going to be here in front of the x, and my b is going to be here in front of the y. The 4 will still be my c. So negative a over b is going to be negative 3. That's the a over 3. That is going to be positive 1. So yes, they do have the same slope, which is required for infinitely many solutions. And then in terms of the y-intercepts, which obviously c is the y-intercept up here, the y-intercepts for line 1, y-intercept is going to be c itself. This guy over here is the b. There's the m. There's the b, the y-intercept. And then for line 2, again, I'm going to use my little shortcut, which is c over b. C is 4 in line 2, and b is the 3, so that's 4/3. So the second line has a slope of 1 and a y-intercept of 4/3. In order for there to be an infinite number of solutions, the 1's have to be equal, which they are, and the c must equal 4/3 because our two y-intercepts must be equal, and c is the y-intercept of the first line and 4/3 is the y-intercept of the second line. That means c must equal, and that is what they were asking here, c must equal 4/3. On to the next example, which again you should probably try to do on your own. So in this example, again, we're given a system of equations. We are told that there are no solutions, and we are being asked for the value of P over Q. Let's recall that for there to be no solutions, again, I'll label these lines, line 1 and line 2. We know that the slopes must be equal. No solutions means parallel lines. So the slopes must be equal, but the y-intercepts must not be equal. Slopes must be equal, y-intercepts must not be equal. So let's deal with the slopes first and see where that gets us. So the slope of line 1, again, I'm going to, since these equations are in standard form, I'm going to use my shortcut once again, which you will be using a lot on the test. So this is going to be negative a over b. A is 2/3, b is negative 4/9. I am not going to mess around with this. I'm going to go right into my calculator, and I am going to punch this in. There are multiple ways to enter this calculation in your calculator. I'm going to do it using my fraction layout just to make this easier for me and to make it a little bit nicer. So I'm going to do negative and then alpha F1, enter, and then I have a fraction in the numerator and a fraction in the denominator, which means I'm going to do alpha F1, enter again. And so in that numerator, I'm going to put a 2 over a 3. And in the denominator, I am going to do negative and then alpha F1. F1 is that little green F1 right there. It's the y equals key. And then what do I got here? I got 4 over 9, and then I'm going to hit enter. So my slope is 3/2, and the calculator did all that work for me. Again, I can enter this in multiple ways. I could do negative parentheses 2 divided by 3, end parentheses divided by parentheses, let's say negative 4 divided by 9, and I get 1.5, which is equal to 3/2. I could also math enter that to get the fractional value. So again, if you don't know or are not familiar with the F1 menu here, you do not need to use that. And obviously, if your calculator does not have that menu, you can't use it. In terms of where to go from here, we now need to deal with the slope of line 2, and the slope of line 2, very simply, is going to be, in this case, we've got an P in our A position, and we've got a negative Q in our B position, and therefore the slope of this line is P over Q. Well, remember, this equation has no solutions, and that means the slopes have to be equal, which means that these two values, the slope of the first line, the slope of the second line, must be equal. P over Q must equal 3 over 2, and what do you know? That is what the question is asking. What is the value of P over Q? So we are done. 3 over 2 or 1.5 would also be acceptable. The answer to the previous question. If you had answered in decimal form, you could have answered 1.33 or 1.333 repeating. Obviously, if this had been a grid-in on the test, the only values that would fit in the grid would be 1.33, and that's what you would grid in, although sticking with the fraction 4/3 might have been slightly safer. On the next page, we talk about the actual methods for solving a system of linear equations. So finally, we get to how we actually solve these things. There are multiple methods for solving a linear system. Algebraic methods, most students, by the time they are sophomores, juniors, seniors in high school, they should be very familiar with substitution and elimination. If these don't sound familiar to you, most likely as I start to go through these processes, you will recognize them fairly quickly, and hopefully they should come back to you fairly quickly. So let's start with substitution. The steps for substitution are listed here. We're just going to work through them one step at a time. So what we do is we pick one equation and we isolate the x or the y. In a quick glance of this system says that it probably would be easier to isolate the y in the second equation. We don't have to, but I think that's what's going to be easiest. So what we're going to do is we're going to write down 6x minus y equals -2. I'm going to add y to both sides, and I'm going to get 6x equals y minus 2, and then I'm going to add the 2, and I get y equals, I'm just flipping the equation around here, y equals 6x plus 2. So instead of this second equation, I now have y equals 6x plus 2. That is step 1. I have isolated one of my variables. In the other equation, this is step 2. In the other equation, what we're going to do is we are going to replace y, the variable that we solved for in step 1, with 6x plus 2. So in the first equation, I'm going to substitute, that's why this method is called substitution, I'm going to substitute for y the 6x plus 2 expression that I just found in step 1. And now what I have is I have an equation with only one variable that I can solve for, the value of that variable x. So what do I do here? I distribute the 2 to those two terms. I get 12x plus 3x equals 9. Combining some like terms over here on the left, 12x and 3x is 15x. I'm going to subtract the 4 from both sides, and I'm going to get 15x equals 5. I'm going to divide by 15, and now I have at least one of my two variables, one of my two coordinates of the point of intersection between these two lines. I have that x equals 1/3. In step 4, what it says is I can find the value of the other variable, in this case the y, by substituting the 1/3 into one of the two equations. And probably the easier equation to use would be the second equation up there, 6x minus y equals 2. I'm not going to use this rearranged form here. I want to go back to the original equation. So I'm going to do, again, this is step 4, where I am substituting the value I just found for x in the second equation. 6 times 1/3 minus y equals, it's -2. So what is this? This is 2 minus y equals -2. I'm going to subtract the 2, and I get y equals -4. Multiplying through by -1, I get y equals 4. And by the way, I could have taken that 1/3 and plugged it into x in the first equation, that would have been fine as well. I just chose the second equation somewhat randomly. So it looks as if 1/3 and 4 are going to be my two solutions that I got using substitution. But what I do want to do is I want to check those values by plugging the values into both of the original equations to make sure that they are satisfied. So in the first equation, 2y plus 3x equals 9. Let me zoom out here a little bit so I can see that. That is going to be 2y, which is, we found to be 4, plus 3x, which was 1/3, and that is supposed to equal 9. Let's see if it equals 9. That is 8 plus 1. 3 times 1/3 is 1. So indeed, the first equation is satisfied by these two values of x and y. The second equation, I know that it works because I used that equation to solve for my y value, but I'm going to do it again anyway. And it should be that 6 times the x value, 1/3, minus 4 should equal -2. And indeed, because this is 2, we subtract 4, we get -2. So the second equation is satisfied, and we are done. You are going to try example 6 on your own right now. Pause the video, do it. In example 6, the question is giving us a system of linear equations. They are telling us that there is a point out there that satisfies the system of equations. We are going to need to find the value of x, y. So clearly we do need the values of x and y that satisfy this system so that we can then find the product of those two values. So we're going to do this using substitution. Again, what variable do we want to isolate? It doesn't really matter. What I'll do is I'll add x to both sides of the first equation, plus x, plus x, plus x, and I will get y equals x minus 2.5. So the first equation, equation 1, is now y equals x minus 2.5, and the second equation is x plus 6y equals 13. So now what I am going to do is I'm going to write x plus 6 times, substituting for y, I get minus 2.5. That calculation without a calculator might get slightly ugly, but we're going to do it anyway. So what do I get here? Distributing, I get x plus 6x minus 6 times 2.5. That is going to be 15. So x plus 6x minus 15 equals 13. Look, in terms of that calculation, the 6 times 2.5, you should be able to do that in your head. There's multiple ways to figure out what that equals. You could do 6 times 25 and then divide by 10, or move the decimal over. You can remember that 6 times 2.5, which it means 1 6, another 6. That's the 2. That's the 2 6s, and then half of a 6 is a 3, so that's 6 plus 6 plus 3, which would equal 15. Again, there's multiple ways to do that calculation. If you get to a point where a calculation is too difficult for you to do in your head, if you're on the no calculator section, you could always go back and see if maybe you want to solve for x in the second equation or something like that. But you're going to run into situations where you have to do calculations like this in your head, so you might as well practice it. So again, what do we have here? We have 7x minus 15 equals 13. I'm going to add the 15, and I get 7x equals 28. I divide by 7, I'm running out of room here. I get x equals 4. So now that I have my x value, remember what I do. I take that x value, I plug the x value back into the one of the two equations to find out what my y value is. I'm going to plug the x value into equation 2, so that is 4 plus 6y equals 13. Subtract the 4, I get 6y equals 9. I divide by 6, I'm going to reduce a little bit. I get y equals 3/2. They are asking me not what x and y are separately, but what their product is. So I do 4 times 3/2, and 4 times 3/2. Again, multiple ways to do this calculation, but 4 times 3/2 is going to be 6. That should be the product of x and y, and I am done. I did skip the checking step here, which I shouldn't have done. I should have plugged the 4 and the 3/2 into the two equations to make sure that they work. Go ahead and do that on your own. Make sure they work. But I think they do. On the top of the next page, we have elimination, which is our other algebraic method that we can use to solve linear systems. We just went through substitution. Now we are going to do elimination, and in elimination we do exactly what it sounds like. We are going to eliminate or cancel out one of the two variables. So the way that we start this is we want to stack the equations on top of one another so that like terms are in the same column. In a lot of cases, you'll get the equations in that way initially. In this example, we do have to do a little bit of rearranging. So what are we going to do here? Let's rearrange both of these so that they are in standard form. So this first one, y equals 4x minus 4. What if we subtract the y? Subtract the y, we get 0 equals 4x minus 4 minus y, and then let's add the 4. Those 4's and y's look very similar. That's a little dangerous. So what do we have now? We have, flipping this around, we have 4x minus y equals 4. So that's the first equation in standard form. The second equation is much easier. We just do minus 3y from both sides. So now we have 4x minus y equals 4, and we have 8x minus 3y equals 11. And now notice that we have the two equations stacked with our, this is supposed to be a y, see 4 and y, got to be careful of those. So we have our x's in the same column, we have our y's in the same column, we have our constants in the same column, and we are ready to go to step 2. Step 2 says that we need to multiply one or both of the equations by a certain number, positive or negative, to make the coefficient of one of the variables the same number with opposite signs. So what I'm going to do is I'm going to multiply through the first equation. Let's do it by negative 2. Because if we multiply that equation through by negative 2, so again, this is the first equation, this is the second equation, then equation 1 becomes, distributing that negative 2 to all of these terms, that equation becomes negative 8x, and negative 2 times negative y is positive 2y, and negative 2 times 4 is negative 8. And now, in step 3, what we do is we add the two equations, and the result of adding these two equations is that the x terms cancel each other out. 8x plus negative 8x is 0. That's the elimination step. We've gotten rid of our x variable. Negative 3y plus positive 2y is negative y, and then 11 plus negative 8 is just 11 minus 8, which equals 3. So that's negative y equals 3, and that means if we multiply through by negative 1, we get y equals negative 3. So that is our y value. We have just performed step 4. We solved the resulting one variable equation for one of the variables, and now what we do is very similar to what we did in substitution. We find the value of the other variable. This is step 5 down at the bottom there, by the way. We find the value of the other variable by throwing that negative 3 back into one of the two equations. I'm going to throw the negative 3 into, let's do it into equation 2. So we're going to do 8x equals 3 times negative 3. That negative 3 value is just going in for y, plus 11. So this is going to be 8x equals negative 9 plus 11. That is 8x equals 2. We divide by 8, and we get that x equals 1/4. We do need to check to make sure all of that works. So in the first equation, we have negative 3 for the y equals 4 times 1/4 minus 4. Is that true? This is 1 minus 4 equals negative 3. Yes, negative 3 equals negative 3. All checks out. Second equation, 8 times 1/4. Again, plugging the 1/4 in for the x equals 3 times negative 3 plus 11. 8 times 1/4 is 2. 3 times negative 3 is negative 9 plus 11 is 2. Again, it checks out, and we are good. So we do have our two solutions, or I should say our one solution. The one solution is that x equals 1/4 and y equals -3. That is also the point of intersection between these two lines. That is elimination. You are going to do example 7 on your own. Pause the video and try it out. In example 7, we are given a system of equations. We are asked for the value of x. So what do we do here? We are going to multiply through, let's multiply through the second equation. If you chose to do this differently, that's fine. I'm going to multiply through the second equation by -2, because what that's going to do for me is make the coefficient of the x, because -2 times 1/2 is -1. The coefficient in front of x in the second equation will be -1, which will be same number but opposite sign. And then when I add these two equations, the x terms will go away. -2 times -y is +2y. -2 times 5 is -2 times 5 is -10. When I add these two equations again, x plus -x, x's go away. 2y plus 2y is 4y, and 8 plus -10 is -2. I now have my y value is -1/2. How do I find my x value, which is what they're asking me for? Got to be careful, they're not asking me for y. The -1/2 goes back into, probably this first equation will be easier. So we have x plus 2 times -1/2 equals 8. That is x minus 1 equals 8. I add the 1, I get x equals 9. That should be the value for x. Let's just check to make sure those x and y values work in the second equation. So what is that? That is 0.5 times 9 minus -1/2. Again, just substituting in the x and the y there. And that should equal 5. 0.5 times 9 is 4.5. Minus -1/2 is plus 1/2. And indeed, that second equation does work. So they wanted x, which means my answer here is 9. At the top of the next page, we talk about some of the other possible outcomes that you might see when you are doing the algebraic methods. We know that there are 3 possible outcomes to linear systems, to a system of linear equations. We just saw a bunch of examples where we did get one outcome or one point of intersection where the system was consistent and independent. Now we need to talk about certain cases where the algebraic result isn't that nice, neat, x equals one thing, y equals another thing. You need to know what you're dealing with if you don't get a result like that. So if you do the algebra and you get a result that is always true, something like this, 0 equals 0. If you do your algebra and you come up with 0 equals 0, either through substitution or elimination, that means that your outcome is infinite solutions. A result that is always true, like 0 equals 0, tells you you're dealing with infinite solutions. If you get a result that is never true, where maybe you've got 0 equals some other number like -6, again, that's just an example, a result like that will tell you you're dealing with the no solutions outcome. No solutions. All right, remember infinite solutions is same line, no solutions is parallel lines. So if you do your algebra and you see one of these two things happen at the end of your work, always true, never true, you have infinite and no solutions respectively. In the no calculator section, you should know that elimination and substitute, we're going to move on to a couple of other methods of solving these systems of linear equations, but you should know that on the no calculator section, the elimination and substitution will probably be your best bet. The calculator methods, which might be available to you on the calculator section, depending upon what kind of question you're being asked, we have actually 2 things that we could use. We have an app called PLYSMLT. If you do have a more recent, more modern TI graphing calculator, you almost certainly will have this app in your calculator. If you just press the app button, which is right next to the program button, I will show you that right now. Your app button is right here, apps. You can also use your graphing screen. So let's go over how to do example 8 with both of these methods. You might want to just follow me through this since this will be new to a lot of you. So we are given a system of linear equations here. We are being asked what the sum of x and y are. So we need to find the solution to this system, the xy point of intersection to the of these two lines, and then we need to add those two values together. So what we're going to do is we're going to use PLYSMLT. We're going to go apps. Number 9 in my calculator is PLYSMLT. You may need to yours may be number 4 or a different number depending upon how many apps you have loaded onto your calculator. So number 9 is PLYSMLT. I'm going to go to simultaneous equation solver. You will recall that earlier in this section I told you that systems of equations are also sometimes called simultaneous equations. So we are going to use, in this main menu, we're going to use number 2, the simultaneous equation solver. In terms of the mode screen here, we do indeed have 2 equations, 1, 2. We do have 2 unknowns, 1, 2, an x and a y. These 4, you can really set these any way you want. I have mine in decimal mode, normal mode, float mode, degree mode. Again, doesn't really matter what those are in, but you might want to set yours up the way mine are so that everything works out the same. I am then going to hit the graph button, which is my next tab. I'm going to hit graph to go to next. And now what I have here is I have a system of equations. Now, if you have an older calculator, but you still have the PLYSMLT app, you may actually see a matrix. And in that matrix, instead of the actual system, in that matrix, you are just going to enter your A, your B, and your C for the first equation. In other words, your 4, your 2, and your 29, and then your 3, your A and your B and your C for the second equation. In this case, it would be a 3, a 1, and an 18. So if you see a matrix on this screen, that's fine. You're pretty much going to enter the same thing that I'm entering. So I'm going to enter a 4, and then I'm going to go over here and I'm going to enter a 2, and then a 29, and then a 3, and then a 1, and then an 18. That's already in there. And now I have in my calculator the same system that I have on my paper, and what I am now going to do is once again hit the graph button to solve, and look at that. I have my x and I have my y. So x equals 3.5, y equals 7.5. By the way, I can convert those to fractions by hitting the graph button again. I will get the fractional form of those two values. In this case, since I'm adding these together, actually doesn't really matter what form these are in. I'm going to do this. Actually, I can do this in my calculator. Why am I doing this on paper? I'm going to do 3.5 plus 7.5, and I'm going to get 11. So 11 is the sum of x and y. In the older calculator, again, your PLYSMLT app may look a little bit different. I will actually show you what it might look like. We will go to apps. We will go down to the P's. We can also get to the P's by doing alpha and then the 8 button, which you can see has a little green P above it. So if I hit alpha and 8, I will go right to my P's, and I can see PLYSMLT right there. So I'm going to go down to it. I'm going to select it. I'm going to hit enter. It's telling me to press any key, so I'm going to press enter again. Simultaneous equation solver, number 2. 2 equations, 2 unknowns. Remember I said these things can pretty much, you don't really need to fiddle around with these all that much, but in this calculator I've got fraction, normal, float, degree, fine. I'm going to hit next. There's my matrix. So I would do 4. That is the coefficient in front of the x. I would do 2. I would do 29. I would do 3. I would do 1, I would do 18, and then I hit solve and I get my 2 fractions. If I hit fraction to decimal, which is the graph button, I get those 2 decimal values. So again, similar process, just interface looks a little bit different, a little bit nicer in the new calculator, but equally as effective in the old calculator. In terms of doing using the graphing screen. You can use the graphing screen to find a point of intersection. For those of you that know how to do this, You can go ahead and try it on this question. If you don't know how to do this, just follow me. The process will be the same on newer and older calculators. It will just look a little nicer on the new calculator. So remember that if we want to graph lines, we have to have our y isolated on one side of the equal sign, which means we need to rearrange both of these equations into slope-intercept form. The second equation, much easier to do. Just subtract the 3x from both sides, and we get that. First equation, a little bit more work to do. I'll subtract the 4x, subtract the 4x. I get 2y equals negative 4x plus 29. Divide by 2, divide by 2. And I actually can just enter this. I'm not going to clean this up anymore, because what I can do is I can enter y equals alpha f1, enter, negative 4x plus 29 all over 2. So I don't need to reduce anything there. I can just enter into the calculator exactly what I see on the page. And then here I have negative 3x plus 18. So now I have the first line and the second line in y equals mx plus b slope-intercept format entered into my y equals menu. I'm now going to go to graph, and I'm going to see something that looks like this. By the way, if your window does not look like mine, you should hit zoom, and you should hit Z standard, number 6. And that should make your screen look exactly like mine. And now what we are going to do is we're going to try to find this point of intersection exactly. I can look at my graph and see that the point of intersection is right around these values, right? I have about 3.5. I have about 1, 2, 3, 4, 5, 6, 7.5 there. So a little visual inspection can tell me that I can get close to the 3.5, 7.5, but I do want to be exact, which means I'm going to use the calculations function right here. So I'm going to do second and then hit the trace button, which will bring up my calculations options, my calculate options, and I'm going to select number 5, which is intersect. The calculator is going to ask me to put my it's going to ask me to put my cursor on the first curve, and it's already on the first curve. I'm just going to put the cursor somewhere near the point of intersection, so I just hit to the right there until I saw my cursor appear. So I'm going to hit enter at that point. It's going to ask me to put my cursor on the second curve near the point of intersection, which I have already done. It has already done it for me, so I'm going to hit enter. The calculator is asking me, do you want me to take a guess? And yes, calculator, I want you to take a guess. And the calculator guessed exactly right. So the calculator told me that the point of intersection was 3.5 comma 7.5. That is my x value. That is my y value. So I have confirmed the result that the app gave me initially. That is how you would use your calculator to find a point of intersection between two lines, or in fact between any types of curves. Now, there's one more thing that we do need to talk about, and that is the fact that you will occasionally see systems of linear equations questions where there's a little bit of a shortcut. So we just used calculator methods to solve example 8. Example 9 is the exact same example, and we're going to go through it again, and we're going to see why it is that solving with the calculator was actually slightly ridiculous, or I should say solving with graphing or with the PLYSMLT app was slightly ridiculous, because there's a really easy shortcut to this question. If you saw it before and you were wondering why I was using the calculator, well, it's because you needed to know the calculator methods as well. But the shortcut here is, if you look at what the question is asking, you can see that if you actually just subtract these two equations, 4x minus 3x, that gives you x, 2y minus y, that gives you positive y, equals 29 minus 18. Well, in your calculator, if you do 29 minus 18, 29 minus 18, that gives you 11, and you are done this question way more quickly than if you had used the calculator techniques. Now, that's not to say the calculator techniques aren't valuable. It's not to say you shouldn't be aware of, know how to use the calculator techniques. You should. It is, though, the case that on some linear system questions, there will be these little shortcuts where if you're paying close attention to what College Board is actually asking you, you may be able to see that you just need to subtract the two equations or add the two equations. We're going to do another example of this on the next page where we talk specifically about spotting shortcuts. So again, before you do anything on a system of equations question, you should always consider what the question is actually asking you. That is key number one, so you should be doing this in general. But on a linear systems question, really take a good hard look at what it is they are asking you, because what they are asking you may be some kind of a rearrangement of, or combination of, or multiple of the sum or difference of the two equations that you were given. Here's what I mean. They are asking us in this question, they give us a system, and they are asking us for 100x plus 40y. Well, again, if we add these two equations, we get 5x plus 2y, that's 2x plus 3x is 5x, 4y plus negative 2y is positive 2y, 15 plus 16 is 31. Look at these coefficients, and it should be clear that if we simply multiply that sum of the two equations that we just found, 5x plus 2y equals 31, if we multiply that by 20, we get 100x here, we get 40y there, and we get over there on the right 20 times 31. Again, multiple ways to do this, but probably the easiest way is to realize that 20 times 31 is the same as 2 times 31 times 10, and 2 times 31 is 62, times 10 is 620, therefore our answer is 620. And we get this very simply and easily. We don't have to use elimination or substitution to find x or y. We just add the two equations, see that the sum of the two equations, we can multiply that sum by a certain factor to get what expression they are asking us for, and we are done. We get 620 and we're finished. On the next page, we talk about translating systems of linear equations. On some systems of linear equations questions, the equations of the lines in the system will not be given explicitly. Instead, what we will need to do is we will need to read a word problem, and we will need to translate the words in the word problem into an equation or an expression. What we are going to do in example 11 is we're going to start just by translating some of these words into equations. When we do this, we do want to use appropriate letters for the unknowns. So when they tell us about a length and they tell us about a width, we should be using L and W, not necessarily X and Y. L and W will be much easier to keep track of. So in examples 11a through D, you might want to do these on your own. Pause the video. So in 11a, the description here, the words here say that a garden has a length that is 9 feet longer than 3 times its width. So that translates into length, L, is 9 more than 3 times W. So 3 times W, and 9 more than that would be plus 9. We also could have done 9 plus 3W. That would have been fine. So this is L equals 3W plus 9. We have just translated those words into an equation, a linear equation. 11b, the total cost of a gym membership consists of a one-time enrollment fee of $60 plus an additional monthly fee of $18. So I am going to do cost, I'll say that's C, that's the total cost, equals is the one-time enrollment fee, so that's $60, and then we have to add to that plus $18 per month. So I'm going to do 18 times M, which will be the number of months. So M is the number of months. If I'm doing this for 1 month, it's $18, 2 months, it's $36, and so on. So I take my enrollment fee, the $60, I add that enrollment fee to that monthly fee, and I get my total cost. So C equals, I'm going to switch this around and do 18M plus 60, just so that equation is in slope-intercept form. Marjorie has a total of 80 cents or $0.8 in nickels and dimes. So what that means is that Marjorie's money, I'll just use M, Marjorie's money is 0.8, and that is made up of, I didn't really need that M equals, but that's fine. 0.8 has to equal 0.05 times the number of nickels, because nickels are worth $0.05, that's 5 cents, $0.05, plus 0.1, that's a tenth of a dollar or 10 cents, times the number of dimes. So that means that 0.8 must equal 0.05 N plus 0.1 D, and I have a standard form equation there. And then finally, Valerie bought 2 types of grass seed for a total of $146. Bluegrass seed cost her $6.50 per pound. Fescue cost $4.50 per pound. So again, there's my total dollars. So that's $146, and that must equal the sum of the total cost of the bluegrass seed. So that will be $6.5 times the number of bluegrass pounds I buy, and I'm going to add that to 4.5 times the number of fescue pounds that I buy. So this is the amount I spend on bluegrass, this is the amount I spend on fescue. When I add those two amounts together, I will get my total 146. So 146 equals 6.5 B plus 4.5 F, and again I have a standard form equation there. Now what we are going to do is we're going to put this all together, and we're going to actually solve a system in example 12 where we were given one more equation that we need to translate to pair with one of the equations that we just made on example 11. So go ahead and read number 12 all the way through and try it on your own. So in example 12, we've got the equation that we did up here in the previous example. We have the 146 that was made up of the amount that she spent total on bluegrass and fescue. We said that $6.5 per pound of bluegrass times the number of pounds of bluegrass plus 4.5 per pound of fescue times the number of pounds of fescue, that had to equal 146. Again, that's the same equation that we had up here. But now we are given a new equation. If she bought a total of 28 pounds of grass seed, how much did she spend on fescue? So this part of the question, this phrase, tells us that the number of pounds of bluegrass plus the number of pounds of fescue had to equal 28, and now we have a nice, neat system of linear equations. Probably the easiest way to do this is to use PLYSMLT. Yes, we could use elimination, we could use substitution, we could use graphing, but because of the way that these two equations are set up, the PLYSMLT app is almost certainly going to be the easiest way to do this. So we're going to do apps, number 9, number 2. Everything here should be good. We're going to hit the graph button. We're going to enter in our system 6.5, 4.5, 146, and then we have a 1 in front of our B here. This is 1. This is 1. So we have 2 1s there, and then we have a 28, and we hit enter and we solve. Now we do need to understand that this X and this Y correspond to what is in this first column, what is in this second column. The calculator is expecting us to put the X terms in the first column, the Y terms in the second column. We put the B's in the first, the F's in the second. That means that X corresponds to B and Y corresponds to F. So we have that the B, the bluegrass, is going to equal 10, and the fescue is going to equal 18. But they're actually asking us, I should have circled this, how much did she spend on fescue? This 18 represents the number of pounds of fescue. So we have to be careful here. What we then have to do is we have to do 4.5 per 1 pound of fescue times 18 pounds of fescue, which means the total that she spent on the fescue here is going to be 4.5 times 18, and we get $81. $81. That's how much she spent on fescue. So that is an example of a question on which we have to translate using the words in the question. We have to translate into a system of linear equations, and then we actually have to solve that system. Occasionally, you won't actually be asked to solve the system. You'll just be asked to set up the system, and you will see a few of those in the homework. That is it for linear systems. I know it is a lot, but as I said at the get-go, College Board will tend to test these linear systems in multiple ways, requiring a depth of knowledge that some students are not necessarily used to on these questions. So it is important that you know all of this information.